Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem minimum array end. And I'm not going to lie to you, this is going to be a fun one, at least for me. I'm going to go ahead and show you two different solutions for this problem. One is, I guess you could call it a brute force solution. It's not like it's super inefficient. It's a little tricky, but it's not that difficult, at least to like wrap your head around. It's pretty tricky to like come up with this, especially since this is like a bit manipulation problem. There's a lot of like math needed for this, but there are some problem solving skills that I'm going to try to show you. And the second one is the more optimal solution. And that's where things are going to get pretty fun. So the problem statement revolves around these two parameters that were given. Let's say in this first example, n equals 3 and x equals 4. So n equals 3 means we want to create a sequence of numbers. You could call it an array. That's how they kind of refer to it. And the order of these elements is going to matter. And so we want to fill these values in. Let's say we filled it in like this, A, B, C. What we want to return is the last value in this sequence. So this would be the value that we return. But it's not just random. You can't just pick whatever values you want to add. We want to define this sequence such that there are two rules that are followed. It's in strictly increasing order, not non-decreasing order, but increasing order. So like this. That's not super difficult to satisfy, but the second constraint is a bit more interesting. If we were to take the bitwise and of all of these, it must be exactly equal to the second parameter x that we were given. And so this at first seems kind of nonsensical. It seems like, okay, well, that's going to be difficult. We're going to need a brute force approach to, how do you even generate every possible increasing order array and then check that the and is equal to this. And not only that, we want this second condition to be satisfied. It's going to be kind of hard for me to like write it out. Let's just say bitwise and is going to be exactly equal to x. So these are the constraints we want to follow. Following these constraints, we want to determine the sequence such that the last value, which is obviously going to be the largest among all of these, the last value is minimized. That's what we want to do. So clearly a tricky problem. But once you get into it, the first solution isn't super difficult. Let's dig a little bit deeper into this second approach and see if we can determine a clue or some kind of observation. Because this isn't super difficult. Like the bitwise and, how would we figure out, like if I had a bunch of values, and let me just kind of arbitrarily draw them like 1, 0, something like this, and maybe something like that. So let's say these are my numbers that I chose. And if I were to take the bitwise and of this, it's going to end up being 0 over here. If I take the bitwise and of all of these, it's going to be 0. Bitwise and of these and these, it's all going to be 0. For one of these bits to be set, for let's say this one to be a 1, we would need all of the bits here to be 1. Let's say like we ended up with a result that looked something like this, like 1, 0, 0, 0. Or 3 zeros, sorry. Let's say this is what we got, and I changed this to a 1. If this is equal to x, what does that tell us? Well, if this is equal to x, then that means that we're basically saying every bit that is set within x must be set in every number in the sequence. Because for us to end up with a result that matches x, we need every bit that is set within x to also be set. That's the only way you'll end up with a result that matches x. So now we know that much. For example, in this case, our x is equal to 4. So in binary, it's going to look like this, 1, 0, 0. Now, we could pick a lot of different numbers that have this bit set. That's the only constraint we have. Every number that we pick now must also have this bit set here. For my A, I could do something like this, 1, 1, 1, and then 0, 0. Since the third bit is set, this is good to go. But why should I possibly choose this as the first element in my sequence? Remember, I'm trying to minimize the last element in the sequence, and I want them to be in increasing order, so probably I should try to minimize every other element in the sequence as well. I think that much is obvious. We want to start with the minimum possible. And what do you think is the minimum possible? Well, this is 4. If I want this bit to be set and any different bit to be set, then the next number is guaranteed to be greater than 4. Whether I pick this, which I think is 6, or if I pick this, which is 5, this bit must be set. So long story short, we are going to start with whatever X value we are given, because we know that this satisfies the constraints. This will allow us to satisfy the second constraint in particular. So now that we know for sure that the first value in the sequence is going to be X, how do we determine the other ones? Well, visually, it's actually pretty obvious. We want to now set the least significant bit. Because right now, this is my X. I can turn it into a 5 by setting the least significant bit. And maybe if our X actually looked something like this, a 1, 0, 1, 1, still, I would want to set the least significant bit. But it gets more difficult when you have an example like this one, or even after this one where we ended up with this. This is 5. Okay, now set the least significant bit again. Well, you end up with something like this, which is 7. So clearly we skipped one. The one that we skipped is this, 1, 1, 0, which is equal to 6. So now it kind of just becomes a game of counting. And so now I'm going to show you something kind of clever. Rather than manually, individually updating every single bit, like if I set this one, then I have to set it to a 1, then I have to update the next one to a 1, and then I have to set the previous one back to a 0, we can do this. We're going to take our X value. I can determine the next element in the sequence by adding 1 to the current element. And I'll end up with this, 1, 0, 1. And so the next element here is going to be 5. And then I'll do the same thing here. I'm going to add 1 to it. I'm going to get 1, 1, 0. That's 6, so I'll be here. You can see that this bit is still set in all of them, so clearly it satisfies this. But there's actually a problem with this approach. Let me show you. Let me change the X. Let's say it looks like this in binary. I add a 1 over here. Okay, so now we know that both of these bits must be set in the solution. So I'm going to do the same thing as before. I'm going to try counting. I'm going to add 1 to this. I'm going to end up with this in binary. And clearly, this one does not satisfy the constraint where both of these bits are set. This is not set. So how do we count, but at the same time satisfy this constraint over here where we guarantee that these bits are set? Well, that's the clever part. There is a bitwise operator called OR, which will guarantee that these two bits are going to be set in the sequence of numbers that we compute. We can count and guarantee that at the same time by just taking the original value X and ORing it, bitwise OR it with the result that we get. So this is what I started with. This was my second one after I added 1 to this. And then I'm going to bitwise OR this with 1, 0, 1. I'm going to get 1, 1, 1 in the output. So this is the second smallest number that satisfies this constraint that we can have in our sequence. And I believe this is 7. I think the previous one here, this is binary 5. And then the next one, we're going to do the same thing. We want our next element to be greater than the previous one. This is the previous one in binary. So to make it a larger, let's add 1 to it. We're going to get this in binary after we do the +1. So this is where we're at. And again, we want to guarantee that these two bits are set in the result. So we will bitwise OR it with that. We'll have this. The result will be 1, 1, 0, 1. This is the third smallest value. This is the value that will go here. I believe it's something like 13. But anyways, this is the brute force O of n solution. Oh, and lastly, what we're actually going to return here is the last element. So therefore, we don't actually need to build the array. We can just kind of start here, then get the next element, and then use this to get the next element, etc., etc. So let's code this up now, and the solution will be pretty simple. We'll start with our result initially set to X, and then we will continuously update it. We want n elements in our sequence. This is the first element, so we really only need to iterate n minus 1 times. And since I'm not actually using this iterator, I'll just set it to an underscore. And so then to our current number, we want to add 1 to it. We want it to be greater than the previous one, at the very least, and this is the smallest number that we can increment it by, and we want to guarantee that every other bit is set. So we can set the result to the OR of it with x. That will guarantee that all those bits are set within this number. And then after we do that n minus 1 times, go ahead and return it. This will actually, I think, get time limit exceeded for Python. Yeah, you can see here for some of the big test cases, it does. So I'll just do this in C++, which is pretty similar to Java. We will create a long and then return that, initially setting it to x. And I'll say something like for int I equals 1. And while it is less than n, because we only want to go n minus 1 times, and increment this guy. And then in here, pretty simple. We can actually, now that I think of it, do this in one line. We can do result plus 1 and then bitwise or that with x. So let's give this a run. Whoops, and in classic Python dummy fashion, I forgot my semicolon. I'm too used to Python. Yeah, you can see it works with other languages like C++ and Java, but it is not the most efficient way to do this, at least in terms of big O. Now, a linear solution really isn't that bad. But how would you possibly go about optimizing something like that? Well, in this problem, I believe the constraint is the numbers that were given will be 64-bit integers. But in any case, when you have, let's say, a very large number like n could have been a big number. Let's say it's like 2 to the 63 or something like that. If this is the case, like that's a very big number, but how many bits does this number have? Well, probably not more than 64 bits, right? So it is actually a dramatic improvement to change this from being a linear time solution and to turn it into a solution where we only count like the number of bits in the number, which is going to be roughly log base 2 of n. This is actually a dramatic improvement. Log base 2 of n is much more efficient. Like just do the math here, 2 to 63 versus 63. This number is much smaller than that. So the best way to explain the next solution, which by the way, it's going to be difficult, so don't feel bad if you feel like it is difficult. Just try to focus conceptually on it. The math is going to be interesting. Let's say that this is the x that we were given. So obviously that's like the starting point that we have, and then there's going to be a bunch of zeros before there. The n that we're given is this. It's going to look something like that. And then n minus 1 is going to look like that. The reason I'm even considering like n minus 1 is because this is like how many times we would increment the number. Like in the previous example, I kind of showed you we're going to add 1 to this, and then we're going to get a new number, and we're going to add 1 to that, and we're just going to kind of keep going like that. Now, it's not obviously as straightforward as just taking this number and adding it to that. If it was, then the solution would be pretty trivial. You just end up with something like this. But we know that the difficulty comes from that second constraint I was talking about that I wrote down here, where all of the bits in x need to be set. So how do we do it? The whole point is that we don't want to have to add this many times because that would be a linear time solution anyway. We're going to do something much more clever. We're going to take this number, well, this number specifically, because this is what we're adding here, and we're going to break it up into its components. You see here that this number is not really 65. It's actually 1 plus 64. This is the 1's place, and I believe that is the 64's place. So rather than adding 1 by 1 to this, why don't we just add this? Like add these pieces to that. And now again, it's not literally as straightforward as adding 1 to this and adding 64 to it, because if it was, we would have just added 65 to that number in the first place. The point of this is that we can add these individually and still validate that these bits are set. Now, that was just like a little bit of the intuition. When we actually get into the details, there's going to be a little bit of binary involved, but here's a visual to kind of make this easy for you. Remember when I started the explanation, I was talking about the least significant bit. We want to set that. We want to turn this guy into a 1. That would be the next number in the sequence. And next, I want to set this bit and then keep this as 0. So basically, you realize the 1s themselves, you're pretty much ignoring them, right? You're literally just changing this into a counting problem where ignore all the 1 bits here, like this number specifically, you have these 3 1 bits, ignore them, just look at the zeros, and you might as well consider them being together, because we're just counting at this point. We'll have 0, 0, we'll have 0, 1, we'll have 1, 0, and 1, 1. There's 4 possibilities for that. And so these are the 3 next numbers in the sequence. But these bits aren't going to be placed together. They're going to be placed separately. That one will go there, and this one will go there. So that's a little of the intuition. And obviously there's going to be more than 2 zeros probably in this number. That's part of the reason I think that they made this like a 64-bit number so that there'd be plenty of bits. So now you know that. Let me draw it another way now. If I took this number and I had like 64 slots for it, I won't actually be able to draw 64. So here's my slots. I have the 1 here, the 1 here, and the 1 here. That basically just tells me that these are blocked. We can't do anything with them. But I have this bit, and all of these here. And using these, I can count. I can go to 1, I can go to 2, I can go to 3, to 4, etc., etc. So now you probably see what I'm trying to do here. I'm not trying to put 1 or 2 or 3 in these empty bits. I'm trying to put 65 in those empty bits, because if I do, I guaranteed that these 3 bits stayed the same, and this was the 65th number after this number, not including that one. So basically, like, this is the 66th number in the sequence. I hope the intuition of that makes sense. Okay, but even knowing that, you could, do 1, 2, to 4, eventually to 8, to 16. You could do that, but that's still counting one by one. So now how do we combine this? How do we take these 2 pieces and then put them here? Well, it's kind of like a 2-pointer approach now, actually. This is the algorithm. Let me show it to you. The main difficulty is going to come from the fact that these are integers rather than like arrays, but still. Imagine we are here. And when I say here, we don't actually have like an I pointer. We would rather have like the number 1 itself, because that's going to look like this in binary. And so for us to extract like the information here, we're going to do a bitwise AND, not super complicated. We're going to go bit by bit in this number, which is X. And we're also going to go bit by bit in this number, which is n-1. And this is what we're going to do. So let me actually write out this number down here. So basically, this is what we're trying to do to visualize it very cleanly. We're ignoring these spots, right? These were the ones originally in the number, and we're ignoring those. That's why I kind of drew over them, because forget that they even exist. We are ignoring them. We are mainly focused on the zeros in that number. And so we're going to move that there. We're going to move this here. We're going to move this there, that there, that there, that there, and then this one there. Now, when I say like moving, obviously if we move this 0 here, there was already a 0 over here, so we didn't really do anything. It's more about moving the ones here. So taking this one, moving it there, and taking this one, moving it over here. So the final answer would be something like this, where, these are ones and all that. I ran this code, this example, by the way. I think this number is 535. So now you have an idea of what we're doing, hopefully, and just to give a tiny bit of the intuition of what I'm about to code up, I'm going to have a number 1, and the rest of these are going to be zeros. And I'm going to use this to tell me like the information here. So in other words, like this is going to be my pointer. I'm going to call it like the bit that we're looking at, but there's probably a better way to name this. I'm just sorry, naming is hard. Actually, to make it clearer, I will call this I_x. So this is the pointer that refers to the x number. And I'll have another pointer down here, which I'll call I_n. This is the pointer that refers to n-1. And so our pointers will kind of go like this. Like I'll have my pointer over here. I'll just say I for short, and then j over here. I'm trying to take this element and put it in the next 0 position. This is not a 0, so I'm going to take my I pointer and shift it over here. My j is still over here. This is a 0, so I'm going to put this over there now. This is a 1 right now, so this will be set. Now my I pointer over here is going to be moved over here, and my j pointer is going to be moved over here. I'm going to do the same thing. I'm going to shift this now over here. Okay, now we found the empty position, so move this guy over there. Well, this is a 0, so that doesn't really do anything, but anyways, we can now shift the 2 pointers. I will be over here now, j will be over here now, and then this is 1, so once again, shift this over here. Okay, so now I will go there, or sorry, this will go there, and then j can be shifted again to be over there. So it's just a matter of shifting these pointers to the left and determining the value that is in this number, the bit rather. Okay, so now to code this up, I will leave the rest of this code here, I guess, but I will initialize my pointers, I_x, which I'll set to 1, and I'll do the same thing with I_n. So remember what these actually refer to. These are not indexes. We're not going to increment this. We're going to shift it to the left by 1 every time. Same thing with the one below it. So we'll have a loop. I'll leave it as, well, I guess we could set it to like while equals true, but what would the condition here be? When should we stop? Well, remember, we just want to take all the numbers in n-1 and sort of interweave them into x, which is our starting value. Once we reach like the most significant bit, we can stop, and that will be the case when I_n is no longer less than the number n. So like this might be shifted all the way to like 64, but once we shift it again to like 128, it's going to exceed n, or maybe be equal to n, and in that case, we stop. If it makes more sense to you, you could write it as less than or equal to n-1, because we already started with the first value. That's why we're doing n-1, because we're trying to get the next n-1 values. Right now, this doesn't look that different from the solution up above. They look like they're going to be the same time complexity, but they're not. You'll see why. First, I want to take the current position in x. I want to check, is it 1 or 0? So I take this and I AND it with the value x itself. So if this is equal to 0, we found a 0 bit. What do we want to do? Well, if the current bit that we're at in n, or rather this refers to n-1, if the bit in n-1 is set to 1, so if n-1 ANDed with I_n is set to 1, then let's set the bit in x. And I have a separate variable for that. I have my result variable for that. So I'll set result equal to result ORed with I_x. Remember that the result started out as x. And this is just 1 itself in the position that we are currently at. And so once we do that, we can say, okay, I want to get the next bit in n-1. We're trying to take the bits from n-1 and interweave them into x. So now that I took one of them, I can go to the next. So I'll set I_n and increment it by 1. Or sorry, I said increment, and that's exactly what I didn't want to do. It will be shifted to the right by 1. So like this. That's where the efficiency is coming from. And down here, we'll do the same thing with the other pointer. I_x will always be shifted to the right by 1, or to the left by 1. And then at the end, we will return the result. You can see that while this code is really concise, it is super complicated when it comes to like the math and the concepts behind all of this. It's not super straightforward that this is a two-pointer approach. But it definitely is. If you look at this code and you go back to the drawing that I had earlier, or especially if you do pen and paper by yourself, which I'd highly recommend, you'll find that things generally add up. And after running the code, you can see here that it does work. It is more efficient than the previous solution. I just think with Python, the runtimes are kind of random and unpredictable. I had a lot of fun making this video, but I'm probably going to get back to some other work that I've been doing, like creating some of these pretty cool courses, I would humbly say. This one about Postgres allows you to learn Postgres directly in your browser by kind of solving these Leetcode style questions. And it's a pretty in-depth course, I would say. You'll actually learn like a lot of the difficult concepts, even indexes and stuff like that. Check it out if you're interested. And there are plenty of more courses coming, object-oriented programming, as well as unit testing for beginners, and a few more.